Hello guys, welcome back to my channel Memo on African Motives. Still working on engineering science N3. So working on motion, power and energy, or motion, energy and power. So actually we managed to work on another class where we had a question paper that we had worked on, and this one is actually from July 2021. So we just need to see how they ask these questions. Okay, so the first question it was actually the first question, and we can see that we've got a total of 15 marks in this question. All question paper got a total of 15 marks. Okay guys, so if you're new to my channel, you can consider subscribing so that you become part of the family, so that you don't miss any of the classes that we shall be having from us on African Motives. So the first question was to define the term speed. Okay, so as we know that speed, that one is the rate of change of distance. Okay, from our N2 formulas, okay, speed is actually the rate of change of distance, where speed is distance over time and is actually measured in meters per second. Okay, that's why it's just 1 mark there. All right, then 1.2, state the law of conservation of energy. Okay, so what do we see about energy? Remember guys, from also our N2, that energy, we can't do anything on it, like we can't create or destroy energy, but what we can do is actually to convert it. Can be converted from one form to another. That is the law of conservation of energy, that it can be created or destroyed. All right, so on 1.3, which is the most important question that I want us to focus on, there we are given that there's a body of mass 5 kg is accelerated from 6 meters per second to 15 meters per second during a period of 20 seconds up an incline, making an angle of 25 degrees to the horizontal. The frictional force is 45 Newton. All right, what do we have there? What do we have actually here? This is a body which is actually up an incline. So it's something like this, up an incline. All right, this incline is making an angle of 25 degrees. Okay, take note about incline is making an angle of 25 degrees there. So this is 25 degrees. So this body is a certain mass, which is actually 5 kgs here. We are together, it has got 5 kgs. Okay, so what we are given about this body, guys, the other information, actually you can just try to list it down, because we are given the frictional force. Okay, so which is the one that is opposite, because this body is actually going up. Okay, so the frictional force is going to oppose this time. Okay, so this is what you're going to have. So you're given the frictional force. What is our frictional force here? The frictional force, which is 45 newtons. All right, so put 45 newtons in this case. All right, what do we have? It was accelerated from 6 meters per second, that is the initial velocity, to 15 meters per second final velocity. All right, so the initial velocity 6 meters per second, final velocity 15 meters per second. All right, what else do we have? During a period of 20 seconds, so we've got the time there. Time that took place is 20 seconds. So that was I think that's the information that actually we have there. All right, so the first question now is determine the acceleration. Determine the acceleration. Okay, so this one, guys, from our formula sheet, is we know that you are given so many formulas that you can actually relate there to which one is the best to use there. But we know that if you're given V, U, and T, we can actually use this formula. V is equal to U plus 80. Okay. So in this case, we need the acceleration. So we can just make A to be the subject. That's a V. Transpose U to this side minus U. Divide by T there. So it's over T, which is going to give us the acceleration. Okay. So that's V minus U, which is a V. From the information that we have, it's 15 minus 6. That's 15 minus 6 over the time. which is in this case we've got the time, which is actually that is 20 seconds there. So you're going to divide by 20, something like that. All right. So if I'm to simplify this dividing properly, I'm going to obtain an acceleration of 0.45. That's 0.45 meters per square second. All right. Or someone can just write this as meters per square second like this. Is one and the same thing. So this is your acceleration. So take note, guys. Acceleration, you can use it from the formula that you're given there from this part, or we can just take acceleration to be the change in velocity. Remember, we said acceleration is the change in velocity over the change in time. Okay, so that's another formula that you could have just used there. You could have obtained the same answer there. Okay, then the distance traveled. Okay, the distance that is traveled, guys, this is the distance which is going to be, okay, so let me just add this acceleration. Maybe it's going to help us to find something there. So acceleration is just a there, which is 0.45, the one that we just obtained now. All right, so the distance that is traveled, guys, this is the object which is going up the incline. So we are talking about the distance that was traveled in between here, up, going up the incline. So that is our S, the distance that we want to calculate. So the object started at 6 with initial of 6 meters, ended with 15 in this time and in this acceleration. So what was the distance for that period? All right, so we can use this formula for distance. This is 1.32. Remember, from our formula sheet, we've got S, which is the distance, which is equal to UT plus half AT squared. Like that, if you cross-check properly. So we can use actually this formula to calculate or to determine the distance which was traveled there. So since we have all these values, we've got u. So we use the formula depending on the information we've got u. Everything is there here. So you're just going to substitute. That's u, which is 6 times t, which is 20. So you've got 6 times 20 plus half AT squared. So our A in this case is 0.45. So you put 0.45 times t squared. So you can just use multiplication so that you don't confuse yourself here. T squared, which is 20 squared. All right. So that's it, guys. This is one thing here. So you're going to simplify. If you simplify this part, you're going to obtain 120 plus this part, you're going to obtain 90. Okay, then let's combine. We are going to have 210 meters. So this was the distance which was traveled here. So this S is actually 210 meters. Okay, I hope it's clear now. 210 meters, like that. That is or S there, which was the distance which was traveled in between the what? In between the time frame that we are given there. All right. Then this case, and guys, you must be very, very careful about this part here. The question is to calculate or to determine the work done, not the weight component, but the work done, not the weight. Okay, so this is the work done by the component of gravitational force. Gravitational force, which means we are now talking about weight. So it's work done by the weight parallel to the plane. So which means, okay, we know work done is equivalent to actually the force times distance. We know that. All right, let's start by that. Let's start by this understanding first, so that at least you can understand what I'm trying to say. We know that on a normal thing, work done is force times distance. All right, that is our work done. So in this case, we need a work done which was from the gravitational force parallel to the plane. Okay, so let's start by the gravitational force parallel to the plane. Remember, if you are working with the gravitational force parallel to the plane, we are going to use W, which is so this part here is work done that you're talking about. Okay, so you're going to use the weight component now. Take note, guys, these W's, don't confuse them. Okay, so I'm just going to use the small letter W for the weight. Okay, this one is for work done, work done, and this one is for weight, the weight component. Okay, we know that the weight that we are going to have is from mg. Okay, that's our weight, but this weight, we are talking about a condition where we need a component of force which is parallel. So from our W, we know that our force, which is parallel in this case, yes, it's parallel. Take note, it's parallel, it's parallel to the plane. So parallel to the plane, we know that F parallel, or which is written as Fs, is equivalent to W sine theta. So this is the force that we are going to have for the work done. The distance now is the one that was moved by the object, which is the one that we had here of 210 meters. Remember, it moved 210 meters up the incline. It was moving up the incline. It moved 210 meters. Okay, so like I said, this is the force which is from the parallel component. So therefore, our work done is going to be the force of the parallel component times the distance up the incline. So we have to find this first, which is the force of the parallel component, which is just like this, okay, which is W sine theta. I think this one we are now used to it from our friction there, from our also this part of N2 engineering science. We can relate from that one. So this is the mass mg. Remember W, that's mg sine. Okay, let me just write the formula before we substitute. So we've got mg sine theta m, which is the mass 5, times the gravitational, which is 9.8 there, sorry, times sine theta. So the angle which is operating in the diagram here, we've got an angle of 25 degrees there. So that's sine 25 degrees. Take note, guys, we are not asked to find the weight component here. We need the work done, so we are going to start with the weight component first. All right, so if you are to multiply this, you're going to obtain something like 20,708 29, something like that. Okay, so if you round off, this is going to be 8. This one is going to, because 2 cannot change this 8, so it's going to be 20,708. I'm just going to use 3 decimal places. Okay, so this is my parallel component that I'm having, which is in terms of the weight, weight component. So we are actually referring to the weight component in this sense, which is the one that we are having there. All right, so now remember the formula that we want here is to calculate the work done, and we said our work done is the times the distance, the weight component times the distance. So for the weight component, remember, guys, don't forget this from we wrote this formula here. Okay, we wrote, so we now have this, and the distance is already there. Okay, so it's a matter of substituting. All right, so we're now going to just substitute here 20,708. This is now work done, not weight, but work done. Okay, times the distance which was traveled by this object, and we say the distance which was traveled by the object is 210, so just going to multiply by 210. So that's how pretty the question was. So you can just multiply these two. You are going to obtain 4348,68, which is work done is measured in joules. It's not weight, this is work done. So work done is measured in joules. All right. So that was the idea, guys, on this question. As you can see, it had a lot of things to take, but once you know that it's work done parallel to the plane, work done, you have to work with force times distance. So the force is the gravitational force, which is from the component of gravitational force there. Take note, work done weight is different. Gravitational force, that's where we are taking our weight from, then we use it to calculate the work done. Okay, then let's move on. The work done, take note, if even for this one, the work done by the frictional force, take note, is the work done by frictional force. So just like what we did, it means this is 1.34. We said work done is always force times the distance, but this time it's by what? By frictional force. So you're supposed to use frictional force. We are done. So we are just substituting here because we have got the frictional force from the list of our information. We have got the frictional force there. Okay, I can't see where I wrote this, but the frictional force is there, which is 45 there. So you've got 45 times the distance that we obtained. Remember, we said, okay, this is where I wrote it. That's our frictional force here, which is 45, and the distance which was traveled here, which is 210. So you're going to multiply by 210. Okay, so if you are to multiply this, you are going to obtain the work done in this case as 9,450 joules. So this is the work done that you are going to have, but due to the what? To the frictional force. So I don't know the way that you can like represent it, but it's just work done, guys. You can just leave it like W like that. It's work done. It's fine like that. Okay. And then the last question on 1.35 is the power exerted by the total force. By the total force, we need power from the total force. Okay. Power from total force. Okay. What are we going to have as power from the total force? We all know that power, which is the total power, actually is equivalent to work done over time. Yes, we know this. Work done over the total time taken, or which is the time there, which is the total time actually. Okay. So now what do we have here? Which work done are we going to use here? Okay, we know that work done is, we do not know the work done so far because there was a work done which was parallel, then there was a work done of the frictional. Which work done are we going to use? Okay, the work done that you are going to use is the work done which is taken from, okay, this is it, guys. Remember, there is a frictional force here, okay, which is going this day. So the force that is going, like the work done, it's from the force that is pushing this ball. We want it to go upwards, which is pushing it, yeah, because the frictional is actually pulling it down against where it's supposed to go. All right, so let me explain this so that you can understand me here. So this part which is going upwards here, because we have got the part which is going up, so we can refer this as our F up as the total that is pushing the one that we are, suppose we'll be having a force that's going to push there. So it's only that we are not having like a force which has got a certain angle. We are talking about the one that is actually taking the force upwards and the one that is now opposing. So if you are to say these two are going to oppose each other, but this is the one that is maintaining our object to go upwards. So this is the force that we can use to calculate the work done, because we need the work done for this object to go upwards. So this work done should be from the force, from this force, because remember guys, we said work done is force times distance, but which force are you going to use? It's important. Which force are you going to use? Okay, so how are we going to calculate this force now? How are we going to calculate this? Okay, so we know that F up was I talk about F up in this case, so this is the one that we are going to use here. All right, so our F up is going to be the frictional plus the one that is in the parallel, because this is also in the parallel. They are in the parallel, so these two are the ones which are opposing in the parallel. So that's why we are going to add the parallel component in terms of force. Okay, so what was the parallel component? Okay, the frictional force is there. It's 45 plus the parallel component Fs. Okay, this is here we obtained here. Before you calculated, remember when we calculated work done on the parallel component, we calculated the parallel component of this one, the weight component first, which is 20,7. This is the one that I am talking about. So it's 20,708. All right, so we are going to obtain the force now, which is making this object to go upwards. Now I think it makes sense. So we are going to obtain something like 65.708. All right, so if this is the force which is making this object to go upwards, therefore we can now have our work done, because we know that our work done is force times the distance over the time which was taken. So this force is the one that is making the opposite. Guys, let's come back here. We need the power exerted by the total force, which means the one that is making the object to move. Okay, so as it is moving, there are these two forces which are actually opposing. The parallel component is opposing, the frictional component is opposing. So this is parallel like this or parallel like this. So they are opposing, they are facing the same direction. And facing same direction, that's why we have to add this, because they are facing the same direction. Okay, so anyways, this is our F up, which is 65.708. Now let's just substitute here so that we can actually calculate our power. All right, so we've got 65, the one that we just calculated now, 0.708 times S, which is the distance. So the distance, remember, when it was going up the incline, it covered a distance of what? Of 210 meters. Okay, sorry for this sudden shift. 210 meters over the time. We already have time. For this period is what? 20 seconds. So you've got to divide by 20. Remember, time is supposed to be in seconds when you're calculating power. So that is what you're going to substitute there. You multiply, then you divide together. There you're going to obtain a power of 689,934. This is what you're going to obtain actually, which is in watts. Remember, power, guys, is measured in watts. So that's how they can actually ask these questions. What you actually need there is to have a clear understanding of the question that you are given and how to attempt that question that you're given. So that's it, guys. Working on engineering science N3. That was it, guys, on motion, power, and energy. We shall meet again, working on more question papers and more topics also. So if there are topics and areas that we actually need to work on, let's meet, guys, on the comment section so that we can know which areas and chapters to focus on and to revise on. From Mason African Motives, till we meet again.